In Washington state, low-voltage contractors, including those who install fire alarm, security alarm, and nurse call systems, are regulated by the Washington State Department of Labor and Industries, or L&I. Different trades have specific regulations. Firstly, fire alarm installers are regulated under the Uniform Fire Code, or UFC. Secondly, security alarm installers are regulated under the Washington State Security Alarm Act, which is Chapter 19.44 Revised Code of Washington, or RCW. Thirdly, nurse call installers are regulated under both the UFC and the State Electrical Code, or SEC. Low-voltage installers have several key responsibilities. 1. They must comply with all applicable codes and standards, including the UFC SEC and any manufacturer specifications. 2. They need to obtain permits whenever required for their work. 3. They must use proper materials, appropriate techniques, and suitable equipment for the installations. 4. They are responsible for protecting low-voltage cables from interference and potential damage. 5. They must ensure that all installations are safe and fully functional. Conduit fill ratios are an important consideration and are specifically addressed in the SEC. Generally, the SEC allows a maximum of 40.0% fill ratio for conduits containing non-hazardous low-voltage cables. However, it's important to note that specific exceptions may apply depending on the specific type of cable being used and the chosen installation method. To avoid conflicts and ensure everyone complies with regulations, coordination and communication are key. Firstly, establish clear expectations and guidelines that apply to all contractors working on the project. Secondly, thoroughly review installation plans and specifications together to ensure everyone is on the same page. Thirdly, conduct regular site visits to actively monitor compliance with the established guidelines and regulations. Fourthly, promptly address any concerns or violations that are identified during the project. The Department of Labor and Industries, L&I, plays a vital role in enforcement. They have the authority to investigate complaints and enforce regulations related to low-voltage installations. If there are concerns about the quality or compliance of work performed by other low-voltage contractors, a formal complaint can be filed with L&I to initiate an investigation. The Washington State Department of Labor and Industries provides valuable resources and information on their website at L&I. The Uniform Fire Code can be accessed through the International Code Council website. The Washington State Security Alarm Act, Chapter 19.44 RCW, is available on the Washington State Legislature website. Finally, the State Electrical Code can also be found on the International Code Council website. Regarding conduit fill, there are specific rules to follow to ensure safety and proper functionality. These rules are based on the National Electrical Code, or NEC, which is the standard for electrical installations in the United States. Conduit fill refers to the percentage of the interior area of a conduit that is occupied by conductors. The NEC specifies maximum fill percentages to prevent overheating and allow for easy wire pulling. The basic rule is that the maximum conduit fill for 3 or more conductors is 40.0%. This means that the total cross-sectional area of all conductors in the conduit should not exceed 40.0% of the conduit's internal area. For a single conductor, the maximum fill is 53.0%, and for 2 conductors, it's 31.0%. These percentages are lower to allow for heat dissipation. Different types of conduits have different dimensions and fill capacities. Common types include electrical metallic tubing, or EMT, rigid metal conduit, or RMC, and rigid polyvinyl chloride conduit, or PVC. Each type has different inside diameters, which affect the allowable fill. Conductors also vary in size, measured in American wire gauge, or AWG. Common sizes include 14 AWG, 12 AWG, and 10 AWG. Each size has a specific cross-sectional area. To calculate conduit fill, firstly determine the cross-sectional area of each conductor. This information is typically available from the wire manufacturer or in NEC tables. Secondly, add up the cross-sectional areas of all conductors in the conduit. Thirdly, determine the internal area of the conduit you plan to use. This information is also available in NEC tables or from the conduit manufacturer. Fourthly, divide the total conductor area by the conduit area and multiply by 100.0% to get the fill percentage. If the fill percentage exceeds the allowable percentage for the number of conductors, you must either use a larger conduit or reduce the number of conductors in the conduit. There are some exceptions to the basic conduit fill rules. For example, Chapter 9, Note 9 provides adjustments for conduits containing different sizes of conductors. This allows for a slightly higher fill percentage in some cases. Dilating factors also come into play. When multiple current-carrying conductors are bundled together in a conduit, they generate heat. The NEC requires that the ampacity or current carrying capacity of the conductors be reduced or derated to prevent overheating. Table 310.15 cone in the NEC provides dilating factors based on the number of current-carrying conductors in a raceway. It's crucial to consult this table when designing electrical installations. For example, if there are 4 to 6 current-carrying conductors in a conduit, the ampacity of each conductor must be reduced to 80.0% of its normal rating. If there are 7 to 9 conductors, the ampacity must be reduced to 70.0%. The NEC also addresses the installation of cables in cable trays. Cable trays are open support systems for cables commonly used in industrial and commercial settings. The NEC specifies fill requirements for cable trays to ensure proper ventilation and prevent overheating. The allowable fill depends on the type of cable tray and the type of cables being installed. For ladder-type cable trays, the sum of the cross-sectional areas of all cables should not exceed the allowable fill areas specified in the NEC. For ventilated trough cable trays, the allowable fill is typically higher. When installing cables in cable trays, it's essential to follow the NEC guidelines to ensure a safe and compliant installation. Low-voltage wiring includes communication cables, data cables, and control cables. These cables are used for various purposes, such as telephone, internet, security systems, and building automation. Low-voltage wiring also has specific requirements in the NEC. Chapter 7 of the NEC covers special conditions, including low-voltage systems. Article 725 covers Class 1, Class 2, and Class 3 remote control, signaling, and power-limited circuits. These circuits are often used for low-voltage applications. Class 1 circuits operate at up to 600 volts and are subject to similar wiring methods as power circuits. Class 2 and Class 3 circuits are power limited and have less stringent wiring requirements. The NEC specifies the types of cables that can be used for Class 2 and Class 3 circuits, as well as the overcurrent protection requirements. Common types of low-voltage cables include CM, CMR, and CMP cables. CM cables are general-purpose communication cables. CMR cables are riser-rated cables suitable for vertical runs in buildings. CMP cables are plenum-rated cables suitable for installation in air-handling spaces. When installing low-voltage wiring, it's essential to use the correct type of cable for the application and to follow the NEC guidelines for wiring methods and overcurrent protection. Fire alarm systems are critical for life safety and have specific requirements in the NEC. Article 760 of the NEC covers fire alarm systems. Fire alarm wiring must be installed in accordance with the NEC and the National Fire Alarm and Signaling Code, NFPA 72. Fire alarm circuits are classified as either power limited or non-power limited. Power-limited fire alarm circuits have less stringent wiring requirements. Fire alarm wiring must be run separately from other wiring and must be identified as fire alarm circuits. Red-colored cables or raceways are commonly used for fire alarm wiring. The NEC also specifies the types of cables that can be used for fire alarm systems, such as FBL, FPLR, and FPLP cables. FBL cables are general-purpose fire alarm cables. FPLR cables are riser-rated fire alarm cables. FPLP cables are plenum-rated fire alarm cables. Emergency systems are also critical for life safety and have specific requirements in the NEC. Article 700 of the NEC covers emergency systems. Emergency systems are intended to provide power and lighting in the event of a power failure. Emergency systems must have an independent power source, such as a generator or battery backup system. Emergency wiring must be run separately from other wiring and must be identified as emergency circuits. Red-colored cables or raceways are commonly used for emergency wiring. The NEC also specifies the types of equipment that must be connected to emergency systems, such as exit signs, emergency lighting, and fire pumps. Healthcare facilities have additional electrical requirements to ensure patient safety. Article 517 of the NEC covers healthcare facilities. Healthcare facilities are classified into different occupancy categories, such as general care areas, critical care areas, and operating rooms. Each category has specific electrical requirements. Critical care areas and operating rooms require essential electrical systems which provide backup power in the event of a power failure. The NEC also specifies the types of receptacles and grounding requirements for healthcare facilities. Grounding and bonding are essential for electrical safety. Grounding provides a low impedance path for fault current to return to the source, allowing overcurrent devices to operate and clear the fault. Bonding connects all metal parts of an electrical system together to create an equipotential plane, reducing the risk of electric shock. Article 250 of the NEC covers grounding and bonding requirements. The NEC specifies the size and type of grounding and bonding conductors, as well as the methods for connecting them. Surge protection is important to protect sensitive electronic equipment from voltage surges. Voltage surges can be caused by lightning, utility switching, or internal equipment. Surge protective devices, or SPD, are installed to divert surge current away from sensitive equipment. Article 280 of the NEC covers surge protection. The NEC specifies the location and type of SPD that are required for different applications. SPD are commonly installed at the service entrance, as well as at branch circuits feeding sensitive equipment. Electrical inspections are conducted to ensure that electrical installations comply with the NEC and other applicable codes. Electrical inspectors are typically employed by local municipalities or state agencies. They review electrical plans, conduct site inspections, and issue permits. Electrical inspections are an important part of the electrical safety process. To prepare for an electrical inspection, make sure that all electrical work is complete and accessible. Have all required permits and documentation available. Correct any deficiencies identified by the inspector. Following these guidelines will help ensure a safe and compliant electrical installation. Regarding the use of J-hooks, it's important to understand best practices and potential code implications. J-hooks are commonly used to support low-voltage cables such as data, voice, and video cables. They offer several advantages over other cable support methods, including ease of installation, flexibility, and cost-effectiveness. However, it's essential to use J-hooks correctly to ensure that cables are properly supported and protected. When installing J-hooks, firstly, select the appropriate size and type of J-hook for the cables being supported. J-hooks are available in various sizes and materials, so it's important to choose the right ones for the application. Secondly, space the J-hooks properly to prevent cable sag and strain. The spacing will depend on the type of cable and the weight of the cable bundle. Thirdly, avoid overfilling the J-hooks, as this can damage the cables and reduce their performance. Follow the manufacturer's recommendations for maximum fill capacity. Fourthly, ensure that the J-hooks are securely attached to the building structure. Use appropriate fasteners and mounting methods. The NEC doesn't specifically address J-hooks, but it does provide general requirements for cable support. Section 300.11 of the NEC requires that cables be supported by approved means. J-hooks are generally considered an acceptable means of support, provided that they are properly installed and used in accordance with the manufacturer's instructions. Section 300.4 of the NEC requires that cables be protected from physical damage. J-hooks can help protect cables from damage by keeping them off the floor and away from sharp objects. However, it's important to ensure that the J-hooks themselves don't damage the cables. Avoid using J-hooks with sharp edges or burrs that could cut or abrade the cable insulation. In addition to the NEC requirements, there may be local codes or standards that apply to cable support methods. Check with the local building department or electrical inspector to determine if there are any specific requirements in your area. When coordinating with other trades, it's important to establish clear guidelines for the use of J-hooks and other cable support systems. This will help prevent conflicts and ensure that all cables are properly supported. In summary, J-hooks can be a useful and cost-effective way to support low-voltage cables. However, it's important to use them correctly and to follow all applicable codes and standards.